to get, try to finish the official things first, then we'll talk about the unofficial things. I'm just flipping through my settlement notes, and I would like to today start with this page 8, and it's about the title is Alternative Consolidation Settlement Analysis. All right? Are we there, guys? At least say that you have this. Okay. All right? Okay, Puzzly says yes. By the way, right before I start, I mean, do you guys like this method of learning? Or do you prefer to have face-to-face? What do you think, Puzzly? Face-to-face is better. Okay, so this is, it's just not my feelings then, right? No, Jana pun cakap face-to-face. All right. Okay. Never mind, we'll talk about it later, all right? So I'm on page 8, and as usual, you must have your you should have this chapter 14. Chapter 14 is has everything about bearing capacity and settlement, right? So you should have that with you or within easy reach. And then you also have your your foundation engineering book by Craig, right? And by now you probably realize that I use all three, and the presentation that I make to you are the main components of what is in that chapter 14 and what is in Craig. And you probably also noticed by now that certain things you find in Craig, I don't bother to talk to you about it because I assume, here's my assumption, I assume that you will read up yourself, and I give you the homeworks that are found in Craig, and you have to, if you by any chance does not read up on that topic, then the homework asks for those things and you have to read up anyway, right? So that doesn't mean that you cannot ask me any questions that you find in Craig that may be a little bit difficult for you to understand, but generally that's how I tend to conduct my classes. Moving on. All right, so here's today what I would like to do with you is this. The main thing today is to talk about this Lamb stress part, which is to be found in 2.31. Okay, if I can finish that, then that would be great. And then I might want to start on also settlement analysis on sand, on granular material. All right. So far, we've been learning about all the settlement calculations based on the clay type of material, the cohesive type of material, all right? So if you recall, the last time I stopped, or the last time I met you, we were talking about the Scampton-Barron method. And if you recall, the Scampton-Barron method is a modification of the odometer method, all right? The odometer one-dimensional consolidation conventional method. So let me remind ourselves again, the one-dimensional method is also known as the odometer method. It's also known as the conventional method. It's one which, you have a diameter about you have a ring about that diameter, which is about maybe 2 inches. 2 inches is 50 millimeter, and you have it about this thickness, and you put clay in it, and then you load it in the soil mechanics lab, right? And then you come back every so often to collect the data for the settlement, all right? Obviously, it's all under saturated condition. If you recall your soil mechanics lab, all right? Now, then we did site investigation. I reminded you again that you need to take samples, and some of these samples you are going to now use it, all right, to measure settlement or maybe some other values that you need, like, for example, C values and P values, which are more related to bearing capacity. But for the odometer test, it's you just test for the settlement. And in your case study, you recall that a sample was taken, all right, and was taken to the lab, and then the engineer, all right, which was doing a forensic investigation. See, your bungalow actually has collapsed in that case, or rather has split into two, right? So then it was an investigation much more like a detective. Under normal site investigation, you wouldn't do that. You would probably have anticipated all these things, all right? And then you would have taken the sample and then do all the necessary tests to then predict what the settlement is before you start loading the actual soil in the field, all right? That's what we normally do. But in this case, for various reasons, which you will recall in your case study, that didn't occur, all right? It was actually, they did everything correct in that case study. It's only that they decided to pump the water out, all right? Okay, now, so one-dimensional method, and then we did the Scampton-Barham. And when we did the Scampton-Barham, we did the calculation, we went through the theories, and then Scampton-Barham introduced to you this parameter nu, all right? And if you can get the nu and also the other parameter A, and use these two charts, and if you have the settlement from the odometer result, you just multiply by this nu, and then you will get your new settlement, which is a modified settlement. Still, when we try to compare, right? When we compare with the observed values, in the case that I was talking last week, we were looking at the Waterloo Bridge in London. There was another bridge, right, which I didn't bother to go over with it, but I did with the Waterloo Bridge in London, all right? And we noticed that, okay, you get your Scampton-Barham settlement prediction a bit better than the odometer result, the settlement, but still quite far off from the observed value, all right? So we were then left wondering what on earth happened, all right? Then Scampton-Barham said, okay, look, if you do this, in other words, if you look at this clay, all right, and then you ask yourself whether it's on over-consolidated clay or normally consolidated clay. The normally consolidated clay, you have sedimentation process occurring over a long time, all right? And then the over-consolidation period, you excavate, and now the settlement is less, right? The settlement is, not the settlement, the stress that the element is now less. So that's what is meant by over-consolidation, okay? So there is a distinction between over-consolidation and normally consolidation. And what is the big distinction here? One is consistently being stressed with time, right? So, if you can imagine, Amy, for example, Fazli is sitting on her shoulders, right? Just imagine, all right? So Amy is one element of soil at the bottom, all right, almost near to the rock. And then Fazli is the next element, say 1 meter away. And then you have Liana, and then you have, I'm just reading off this name, right? Then you have Fazli on top of it again, then Nurjana, right? So, and Amy is at the bottommost, and she is like, what do we call it? She's holding everybody up, right? You imagine that element of soil where you say gamma multiplied by z, right? And all this element is all the way column of soil right up to the surface, right? So yeah, right. You have this compression of the surcharges on top of each element, right? So that's what happened over time. So Amy is there over time, fine, and next one was Myra, and then Mira, and then Amy, and then, not Amy, then Rohimatu, right? And as you get nearer to the surface, obviously it is less weighty, right? Less stress, right? Because now the depth is shallow, right? Compared to Amy down there at the bottom, right? So this is normal. Amy would have settled down first donkey years ago. When I say donkey years ago, when the dinosaurs just died, the meteor it just came, and then it became too cold. The dinosaurs died, and then it snowed, and then over time it became spring again, right? Global warming, and then all this soil is being dragged by the snow, and then finally it reaches the surface of the sea, and then it settled down. All right. So the first thickness is Amy, then the second thickness is Mira, then the third thickness is Rohimatu. Okay, so this is over time. I've already said this to you, so I'm just reminding you about it. Okay, this is normal. Now you come along and you excavate that clay layer. All right, that clay layer. So now Amy is still down there, but you have removed Mira, you have removed Rohimatu. So now Amy says, wow, tak adalah berat sangat dah. All right, less weight on her. All right, less weight on her. And why did you excavate? One of the reasons is because you want to make a car park. All right, you make a car park, so you have less weight, less pressure now. Okay, so this is abnormal. All right, it's not all the time that the element of soil is being excavated, right? Not all buildings have a car park underground. Okay, so the normal one, we call it normal constitution. The one which we excavate, we call it Hoover Constitution. Now, okay, so according to Scampton and Theorem, all right, whether you remove the stress or you don't remove the stress, in other words, you consistently stress the soil, has a bearing on the settlement. So this gives you an idea now, right? Gives you an idea now that, okay, that's why the results are not that great, all right? And they are not that great because how you stress the element of soil is also an issue. So it's not enough to know that it's clay. It's not enough to say that it's one-dimensional constellation method, one-dimensional only, all right? The other thing you need to know is that how you stress it. And then whether you say it is one-dimensional or you take into consideration that maybe you need to apply the understanding in terms of 3 dimensions. So page 8 to 13 is trying to capture this idea. All right, page 8 to 13 is trying to capture this idea that you must take into account the stress history. How you stress an element of soil will inform to you the consolidation settlement. Okay, so all that, what have I just said? To summarize, you now know why you're moving from one-dimensional consolidation. You are moving from that idea to a modification by Scampton and Theorem. You're still not happy with that modification, and you're saying to yourself that it is because of stress history. You need also to take into account. So page 8 to 13 is how to capture that, and we capture that by drawing what we call this stress path. I know you do a lot of that in your soil mechanics too. At least you did some of it with me, right? Because like I said, there was this transition of the curriculum, right? So I did a bit, but I think you do a lot more by the time you get into your soil mechanics too. And I think you did consolidation a lot more as well in soil mechanics too. Am I right there? Consolidation, yes? Okay, perfectly good. So if you forget some of these things, then it's a little bit harder in foundation engineering. But as we say in English, don't fret, don't whine. If you forget, you try to find the time to remind yourself on all of those things that you forget, which is what I tend to tell you anyway. So now in coming to this stress path method, we call it the Lamb stress path method. The guy who bring out this idea to us is a person by the name of Lamb. Now, why am I referring to the name? Because Lamb has a different definition of the coordinates that you use, all right? Because I'm sure you did with Dr. Nick or maybe even Dr. Haslinda, right? Other stress path definition. You can draw the stress path using S and T's, all right? But I'm using this P's and Q's. But the P and Q that I'm using is being defined by only two parameters, not two parameters, two parameters, if you like, through two parameters, which is defined by the vertical stress and the horizontal stress, which in other words is the major principal stress and the minor principal stresses. Okay, all right. Now, LAM generally uses that stress path. You can draw the same things that I'm drawing, that I'm going to be talking to you today, using other stress path definition. You can use S and T's, for example. All right. Okay. Now, before I go into all the other details, because I tend to lose people when I talk about the stress part. Why am I losing people? Because they, it's a bit dry. It's just stresses and how it responds, and then how we then relate it to the diagram, to the stress path, and then what it all means. Okay, but just imagine that I took some time to explain to you. You have an element of soil, all right? Now, that same element of soil, you're going to put a building at the surface, all right? Any building, if you like, or any stresses at the surface, and that element now is going to experience the load that you apply, all right? And we are trying to now capture that load that is being applied to the element while consolidation is occurring. Have you gotten that? Yeah, I took a long time to give you an introduction, so I hope you know what I'm saying. Yes? Or no? Or I'm losing you. Mira, ha, ha. Okay. So you now know what you need to do. All right. If you don't get what I'm saying, then you need to deduct quite a lot. Okay. So that's the way things are. Okay. Now, page 8. Before I go into the what do we call it? The stress path diagram by Lamb. All right. The stress path diagram by Lamb. I'm going to review some of the things that you should know, but I know sometimes you forget. All right. So I'm on page 8. All right. Now, for one-dimensional constellation. All right. One-dimensional constellation, I have this ratio of the horizontal stress over the vertical stress. Now you have to have your element of soil. If you have forgotten what I am referring to, right? You must have your element of soil. Okay, you have your surface of soil, and then you have the element. You should draw your horizontal stress and your vertical stress. Can you do that? And then you compare with what I have. It doesn't matter if you are right or wrong, because nobody is going to see it, right? You are going to see it yourself. So I want you to do it so that you at least, do something to your brain. Can you do that? I give you like 2 minutes. Put an element of soil beneath the surface of your soil. Your soil now has to be clay, right? It obviously has a water table at the top, right? If you have forgotten, you're going to have consolidation, okay? So put just a water table there, right? Just to remind ourselves at the surface. Then you have an element of soil. Say to me that you have done it. Yes or no? Otherwise, I'm thinking that you're asleep. Mira says yes. Good. Skandar says yes. Okay. Anyone else? No. Abby says yes. Okay. I hope you can see this small little picture at the side here. All right. Here. Do you see it? I just have an element. I put my vertical stresses and I put my horizontal stresses. Right? Ayn says yes. Ayn, can you see the small little diagram or not? It's usually Ain yang tak nampak tu ni. Yes, Ain? Fazli says yes, I don't know whether he refers to atas sikit sir. Naik atas sikit. Okay. Ain says yes, nampak. Alright. By the way, guys. Right, Amy says yes. By the way, right, this what the heck? I have my WhatsApp, it keeps coming up on the phone, right? Ini digress, yeah, right? I'm just taking a digression. It keeps coming up. When it comes up right in front of this phone, do you see me or you don't see me? You keep seeing me. That means the WhatsApp message doesn't block my face. Is that what you're saying to me? Okay, fine. All right. Okay. Iza, stop. Iza, explain to me how I can, and I'm taking 2 minutes break, Sujab. Explain to me how I can stop the WhatsApp messages from coming up, giving me notification like that. No, why me? Because I feel like doing it. Then I know you're half asleep or wake up, You cannot explain, you mean. What is TP? I'm wide awake, crying face. You don't have to explain through words. You can explain through typing, Anyway, fine. Iza tak mau, doesn't want to do it. Arman, later on, maybe you can explain to me orally, right? So I'm just like taking 2 minutes break. My 2 minutes is up. Now, the ratio of the horizontal stress to the vertical stress is what we call K naught. Now, K naught is the coefficient of earth pressure at rest. You will recall in soil mechanics 2, you also have K sub A and K sub P, the active coefficient, right? And the K sub P, which is the coefficient of passive pressure, all right? Now, this K sub naught is coefficient at rest. It is in between K sub A and K sub P, all right? Now, if I give you 30 degrees, P is 30 degrees. If you recall, what is the value of K sub A? If you don't recall, say, sir, we forgot. Tak ingat, Fazli. Okay, the formula is 1 minus sine P over 1 plus sine P, active. Alright? Active, 1 minus sine, active, 1 minus sine P over 1 plus sine P. Okay, Zab. Tadi kata tidur. KP, alright, KP is the inverse of KA. Focus. KP is the inverse of KA. That means 1 over KA. So if P is equal to 30 degrees, this is just to remind you, what is the value of KA? Tak tahu, lambat. KA is equal to 1/3. Good, Fazli. So KP, tak payah calculate. Tengok je situ tahu dah. KP, AB says 3. So, right. So now you imagine if P is 30 degrees, right? KA gives you 1/3. KP equals 3. So KP is always bigger than KA. Alright? KP is always bigger than KA. Now, why am I talking about KP bigger than KA and all this, trying to remind you that this KP is to do with the failure of soil. Again, I'm talking to you about element of soil. All right, element of soil, you have sigma V and sigma H. And this KP, right, is related to that sigma V and sigma H. KP, right, you multiply by gamma and Z, you multiply by the stresses, it will give you failure. Now, if you recall in soil mechanics too, okay, KP, what you normally, some lecturers, they teach you this way, all right, which is the easy way to teach, because then, they don't have to explain much to you. All right, you have an element of soil in front of a retaining wall or at the back of retaining wall. All right, if I have the retaining wall at the back, sorry, if I have, here's my wall, I have an element here, all right, here's at the back of my wall, and then I have another soil here, or let me just say the soil is all here, okay? So I have my element. If I push this wall towards the element, see, I'm pushing it towards the element. So now my element of soil is being compressed, all right? It's being compressed. So if I keep pushing, ultimately this element or this soil at the back will fail. Only that it fails through compression, all right? It fails through compression, and this is active, all right? It is active, and you see that Ka is only 1/3. It doesn't take much to compress an element of soil, and then it will fail. All right. Now, if I move this retaining wall away from my element, see, I'm moving it. Now, the soil is also being made to fail, but now it fails through yielding. In other words, my element of soil is now increasing in volume. All right, increasing in volume. So that's why the Kp is 3. Now, in between these two types of feeding, you have K0. K0 is the coefficient of at rest. In other words, you don't do anything to it. All right, at rest means it's, you know, you have your element, it's just sitting out there, it's just sitting nicely. All right, that is why you have this ratio sigma H over sigma V is equal to K0. You will see later it's always a constant value. All right, it's not a function of phi. Okay. All right, so I'm just trying to put all this thing into your head. Now, here's your element of soil. All right, element of soil, you have sigma B and you have sigma H. Sigma B is in this direction, okay, for the active case. If it is in this direction for the active, for the passive case, it is not sigma B anymore. This is sigma horizontal. This becomes the minor principal stress. All right, so I'm just trying to remind you again on that. Now, if I have an active situation, this is vertical, this is horizontal, all right? In our calculation of the settlement, all right, the odometer test, whatever, you know, the prior method that we used to measure the settlement, we said that the settlement in this direction, we just don't bother about it. Basically, we say it's 0, even in this direction, all right? It's also 0. So I have only in the vertical direction. If I call that direction Y, say, okay, then this is X and then that is Z. So only bother with the vertical direction. Okay, so that's why you see the strain in the horizontal direction, right, on page 8 is 0. Now, get it into your head that a stress path is the locus of the peak or top of Morse circle. Okay, it's the top of the Morse circle. So I am going to have the peak, and then I'm going to find the coordinate of that peak, and then I am going to connect the top of this Morse circle from one Morse circle to another. Now, what is a Morse circle? Morse circle is a representation of the stresses, right? A representation of the stresses on an element at a particular time. Okay, so here's my element again. It is subjected to some sigma V and to some sigma H. I can calculate the sigma V. I can calculate the sigma H, right? The sigma H, if it is active condition, it is related to the sigma V by K sub A. If it is a passive condition, it's related to the by Kp. Otherwise, it's just K0. All right. Now the stress is usually the first time you learn stress, all right, is usually you learn to reflect it, okay, to capture it, if you will, through this graph, which is the Morse circle, all right? The first time you learn about stresses for an element, and then you learn to draw Morse circle, whether it is a material called concrete or material is called soil, all right? So doesn't matter. All right. So if you look at that Morse circle, I have shear stresses against normal stresses. The shear stresses is on the vertical axis. All right. And then the horizontal axis is sigma. Sigma is just the vertical stresses, right? Or the horizontal stresses. Sometimes you refer to this as normal stresses, right? Okay, so I have the sigma 1, and this is reflected in the active case, right? Sigma 1 is the vertical stress, so it is the major principal stress, and sigma 3 is the horizontal stress. Now, if I have just the K0 condition, okay, element of soil is in K0 condition, meaning pressure is at rest. So sigma 1, usually you multiply the unit weight. All right, let's assume that now you have a soil of uniform homogeneity, right? So gamma is consistent, not consistent, is constant from top to your element. Z is the surface distance, say, from the surface to right in the middle of the element. So if I have just here my element and I put it right in the middle of that element, where is my element? Here is my element, right in the middle, right? So I have from the top to that middle is my Z, okay? And if that unit weight of the soil is gamma, I can get sigma 1 as gamma multiplied by Z, all right? So that's the vertical stress. And if I say that sigma 3 is related to sigma 1 by some coefficient. Now I have said to you earlier that this is at rest condition. So I have sigma 3 over sigma 1 is equal to K0. So sigma 3 is equal to K0 multiplied by sigma V. Are we okay? Or am I losing you? Izar says yes. Yes meaning what? I'm losing you or you're okay? Yes for okay. All right. Jana said too fast. Jana, you have to follow my train now, because we have only got 3 hours, right? And then I'm only talking about things that are in soil mechanics too so far. I haven't spoken about anything new. All right. So even if you miss this, it's not a big issue, because you can follow it up later by yourself. All right. Now it's either too fast because I'm speaking too fast in English, or you want me to speak slowly. Abby seemed to understand me. Amy, haha. Mira says too fast, furious. I'm not driving a car, Mira. But at least slowly. Okay, I'll try to remember that. I've always said to you that when I speak in English, you tend to lose me or I tend to lose you. Okay? Ada rekod tak yang tadi? Okay. Now, you know that when you draw this Morse circle, ini benda lama ni, this you know, right? When you draw the Morse circle, I can draw a line tangential to the Morse circle. Yes or no? Right? I can draw a line tangential to the Morse circle. This is the shear stresses, right, that will cause failure. And this line that is tangential to the Morse circle, it intersects the vertical axis at a cohesion you call C, right? This parameter you call C, cohesion. And then this straight line, right, which is a tangential to a Morse circle, you can reflect it through this formula. Now that formula says tau equal to C plus sigma tangent T. Now you look at that formula. C is the cohesion. That is you remember your bearing capacity? In order to find bearing capacity, you need to know the C value, the cohesion value, whether it is undrained or it is not drained. Right? Then the other parameter, you need to know about bearing capacity, you need to have P. P is the angle of internal friction. Okay, C is that thing that that gives you your cohesion. See, the gum, the glue, if you like, for a small particle. It's not a good way of learning things by saying glue, but I'll take it the easy way to tell you that it's the glue. If you have clay, right, you put some water on it, you feel that the clay is sticky. All right. Okay. Phi is for a grain, right? Particles. I've already explained this many years ago, right? At least 2 semesters ago to you. Now I'm reminding you that I have a particle, I have another particle. If I apply a load to this soil, they will feel crushed, right? But they need to move over each other because I'm compressing them. They need to move, right? So as they move, they are building friction over each other. That is the thing that is giving you the phi, angle of internal friction. That's what is meant by internal friction. Okay? I'll just use the Malay word, right? Geseran dalam. Sudut. See? Sudut, geseran dalam. Because, again, you are applying stresses to this element. Don't forget that. All right? So that is what is happening. Now, this shear stress tau, all right, on the principal plate, you know what the value is from soil mechanics 2. You can calculate that. If you know your C, you know your P, you can calculate to get your C to know whether your element, all right, will fail at what magnitude. Am I right to say that you learn all of this in your soil mechanics 2 and in your other class? I don't know what you call it, mechanics of materials, strength of materials. Yes or no? Okay, Akmal says yes. Everybody says yes. So I'm just reminding you about this. Okay. Now, you also see in that equation, all right, you find the shear stress, you have C and you have sigma tangent P. All right, sigma, that combination of the vertical and horizontal stresses also goes into the equation. Okay, guys? So, reminding you about all of that. Now, you have the peak of the Morse circle. You have the sigma 1 and sigma 3. Now, okay, I want to draw the stress path as what the note says. It says locus of peak of Morse circle, the top of the Morse circle. So if I look over the next page, page 9. I'm on page 9 now. Follow me, guys. All right, you're on page 9, right? Now, on the same Morse, sorry, not on the same, but on the same the horizontal and vertical stresses, right? The vertical, sorry, not the vertical stress, on the horizontal and vertical axis. That is what I want to say, axis. So I still have the vertical stresses, it's the shear stress. Okay? And then I still have on the horizontal axis is the normal stress. Okay? All right, I know that from principle of effective stress, right? From principle of effective stress, I know that total stress, sigma is equal to, sigma prime is equal to sigma minus U. So I have effective stress is equal to total stress minus pore water pressure. So if I draw a Morse circle, that is a total stress, then the only thing that is different, all right, from that Morse circle, because all the stresses are still the same, it's only the pore pressure, right? So sigma prime is equal to sigma minus U. So I would get those two Morse circle, and all they are doing is that it is just being separated by a pore pressure that is U horizontally, right? Now I have the total stress. Okay, the total stress is on the right. Yeah, I have to show this. See, that's the big. Yeah, sigma is sigma U. No, sorry, Fadli. U is pore water pressure. Okay, not sigma. All right, just by the pore water pressure. So Fadli is at least awake. I know he's awake now. This is the effective stress. This is the total stress, more circles. So they are going to be separated by only the pore water pressure U. And I'm just going to consider at the top here, so it's easier to see. Okay, so this is the pore water pressure. All right, sigma prime is equal to sigma minus U. So this is always the case to be. Okay, this U is a constant. All right, so I want you to take like 2 minutes, for example, or maybe 3 minutes or 4 minutes, right? You can like determine the coordinate here. This is the total stress, the coordinate at the bottom here. So, I mean, that's the easy part. The y coordinate on this horizontal axis is going to be 0, yes? Are you able to see this? All right, that's easy to get. Okay, now there is the x coordinate for this point here. All right, so the x coordinate for that is going to be sigma 3. This is the distance from 0 to this point here, sigma 3. All right, so it's going to be sigma 3 plus the radius of this Morse circle. The radius of that Morse circle is going to be sigma 1 minus sigma 3 divided by 2. Okay or not? All right. Radius of that Morse circle is sigma 1 minus sigma 3 divided by 2. So, the coordinate on the horizontal line is going to be sigma 3 plus the radius, which is sigma 1 minus sigma 3 divided by 2. So, this coordinate should be sigma 1 plus sigma 3 divided by 2. Are we all... Can we all get that, or do you want me to calculate it one by one? Nobody is saying anything. Isa, are you still awake? Okay, she said yes. So, sigma 3 plus the radius of the Morse circle, which is sigma 1 minus sigma 3 divided by 2, will give me sigma 1 plus sigma 3 divided by 2. Don't bully me, sir. I haven't bullied you yet. Soon I will bully you. Okay, da? Yeah. You're joking with me, right? Okay. So we have sigma 3 plus sigma 1 minus sigma 3 divided by 2. Okay, now you're laughing. Sigma 3 plus sigma 1 minus sigma 3 divided by 2. Okay, the radius. So we should get at this. This is easy, right? No problem, right? Okay. This one here, I should get that. So I should get these two coordinates. See, this is the thing about this, this online remote learning. I don't know how you're responding to me. All right. So I cannot say your forehead is like frowning. All right. Amy used to make that a lot to me. So I don't know whether you can follow me or not. So all I can see right now is my own face. Who wants to see their own face all the bleeding time, right? Aha, okay, Mira, fine. Okay, so then I will be able to say that at the top here, all right, it will be the same, right? The coordinate here will be sigma 1 plus sigma 3 divided by 2 for the y coordinate, because it's just the radius of the Morse circle, right? And then that is just the radius. Sigma 1 minus sigma 3 over 2 is the radius, right, for the y coordinate. And then I have the x coordinate, which is the same as this one, right? Now, what have I done? Nothing much as identifying the coordinates. That's very straightforward, should be straightforward, all right? And the important thing here is to define the coordinate at the top of the Morse circle. All right. So now I'm moving away, guys. I'm moving away from defining failure as tau equals to C plus sigma d tangent P, right? Which is the shear stresses and the horizontal and the normal stresses, and I have the cohesion and the P value. Now I want to form, all right? I want to form a locus of the path from one state of stress to another state of stress. Here is a picture of one state of stress. And all that is different in this picture here by this circle is that one is a total stress, the other is just effective stress. Okay? Now, right. So I have defined the radius to you, sigma 1 minus sigma 3 divided by 2. I'm going to call it a name now because sigma 1 minus sigma 3 divided by 2 is too long for me. Okay, I'm going to call it Q. And by the same reasoning, I will call the other one P, which is sigma 1 plus sigma 3 divided by 2. All right? And then I will call P prime, the effective parameter, sigma prime 1 plus sigma 3 divided by 2. Now the question then is that why is there no Q prime? All right? Because after all, the principle of effective stress, all right, applies all the time. It doesn't matter whether you call it QPRS or whatever you call it, because stress minus water pressure will give you the effective stress. Well, the bottom part of page 9 shows to you that the value of sigma prime 1 minus sigma prime 3 divided by 2 is the same as sigma 1 minus sigma 3 divided by 2. In other words, mathematically, they are the same. Q equals to Q prime. Okay? So now I can have the plot of my stress path in relation to the top of my Morse circle represented by Q, P, and P prime. No Q prime because Q prime equals to Q. Are we okay? Now, which is what this picture is all about. Figure 14.6. Yeah? Figure 14.6 is this picture of what I just explained to you. In other words, I have on that figure 14.6, not worried yet about what exactly is happening, but you can look there. I have my original Morse circle. I still have my original Morse circle because I want to relate to earlier on. I said to you that, a Morse circle is just a representation of the state of stress for an element. Okay, so I still have my Morse circle there. But not only that, I have my total Morse circle, right? Total stress Morse circle. I also have my effective stress Morse circle. And they are just distinguished or differentiated by the difference in pore water pressure. All right? Because the pore water pressure is constant. So if I have here, M and N, that's just the one state of stress of an element of salt. One is in total stress, another one is in effective stress. Okay? And they are just separated from each other by the pore water pressure, mu sub I. The other one here is another state of stress. All right, we have moved to another state of stress. We have loaded it or unloaded it. All right, and we have, Q and R again being separated by the pore water pressure. It so happened that now in that diagram in figure 14.6, you now have a final pore water pressure. All right, because you have gone through many stages of applying the stresses. Okay, so now you have the indication. Are we okay with that? Because I just want you to know what the destination is before before we go on further. All right. So now on page 10. Page 10. All right. When I'm in class, I think I'm taking 1 minute break, right? When I'm in class, Mira doesn't open her mouth. All right? She's just very quiet. I have to push her, talk to her, and she still won't talk to me. All right? Occasionally she will. Now, Amy is saying, ha, ha, ha. But when online, she is so active. It's like her fingers is doing the talking. Yeah. See? For mirror, it's like, they have a way of teaching whereby you can use your handphone, all right, and then you will respond, right? Because some people are like that. I'm not saying that mirror is bad or anything like that. I know that from my interaction with so many other lecturers, I go to so many seminars, and we're always trying to improve our way of teaching, right? One of the things that we have to know about, right? So they are in some universities, all right, they will ask a question and you can respond through your phone, because some people are like Mira. Okay, ni apa pula kena lagi, ni just giving an example. Okay, right, Fazli is now laughing, ha ha ha. Okay, right, now page 10. All right, page 10. Some people are like that. They're just different. Okay, right. It's like some people, I can remember their faces, but I can never get them to say anything. Right? You know who those people are, right? In the class. So there's nothing I can do for that, right? I'm not blaming them. I'm just saying that some people are like that. Now, okay, how about page 10? All right. So I don't have to put on my axis Q prime. I need to put Q though, because they're the same thing, right? Now I just need to plot the locus of top of the Morse circle, and with the axis P and Q, right? And then if I can plot the points, all right? I can draw the path. Then I got my state of stress. In other words, I'm saying to myself from the days, say, all right, when the dinosaurs just died, to now when I'm excavating, I can plot the history of how that element, okay, that element has been stressed. Are we okay? All right. Now, why do I take the bother to explain all of this? Is because you see this picture again. Now you remove the Morse circle, and all you will get, if you remove all this Morse circle and all I have is my Q's and P's, all I will have is just a line. I will have a line NPR, and that line has that arrow symbol that says that from N go to P, and from P go to goes to R. All right. In other words, if I were to draw, where can I draw? Let me have a piece of paper. This is all I will have. See? Okay? Can you see? NPR. Fazli says okay. Right? You see the thing that I'm seeing now, it is laterally inverted. I don't know what you say that in Malay. This picture here is the opposite of what I see. Do you see the opposite as well? Laterally inverted. Do you guys know what I'm talking about? Okay, if I hold this picture in front of a mirror, okay, from camera makes the image inverted. Akmal, okay, Arman says that. Front camera makes the image inverted, all right? But do you see this inverted as well or no? If I were to look at it, it's not what I see in this picture, right? Okay, so you know what I'm saying, right? All right. Okay, so you're seeing the real thing. I'm not seeing the real thing. I'm seeing this, laterally inverted. So anyway, this is all I'm seeing, as opposed to, like, where is my picture? Here. See? All right, two different things. The proper way of drawing it is this one. All right. But so why am I showing to you all of this? Because when I look at this one here, I'm thinking that I have all the stresses, I have all the Mohr circle, I am connecting the top of the stress part. Okay or not okay? Iza says not clear. What are you not clear about? Now she's not responding to me. I'm waiting for her. The picture tak nampak sebab warna paper tu biru. The paper is not blue. The paper is green. You are seeing blue. See? Amazing. Saya rabun. What is rabun in Malay? In English? Saya pun nampak biru. Okay. Blue lah sir. No merah, it is green. I know in the picture it's blue. But in front of me, it is green. It is light green. Okay? But it doesn't matter. It is light green. Anyway, you cannot see you cannot see oh, okay, yeah. Is it green or blue? Aqua. Okay, good, Mira. This is now definitely. Okay, Fazli Sigaret. Okay, can you snap the picture and send to Shakila? No! I'm going to feel bad. Why am I going to not take the picture? Because here is the picture. Here is another picture. Imagine if you only have points. You don't have circles. You have Q and P. Can you imagine that? Yes or no? And why won't I send you a picture? Because here's another reason. If I can get it to it. Okay. I'm now on page 257. Can you open 257 of Craig's book? Yes? Okay. Or better still, page 262. Page 262, what do you see? You only see lines. Yes? Okay. So, but at each of those points on page 262, right? At A, B, C, D, E, for example, all right? They represent what? They represent the top of a Mohr circle. And what is a Mohr circle? A Mohr circle is a representation of a state of stress. It has horizontal stresses and vertical stresses. So A is a representation of sigma V and sigma H at some point in time. And the same is happening at B. But A and B are the top of a Mohr circle, not tangential, not anywhere else. That's what I'm trying to explain to you. Every time I see that dot, A, B, C, D, E, I'm saying there is a sigma V, sigma H at that point in time. Not only that, there is also a pore water pressure acting at that point in time. Okay? All right. All those trouble I took was to explain to you that. Now, if you look on page 267, you see on page 367, they are nice enough to still show to you the stress, the Mohr circle. Okay, so that to remind to you, all right, each of those points are a state of stress, having vertical stresses, horizontal stresses. And from each of those state of stress, you will move to another state of stress, and you can connect this point. And they call it a stress part. So now I'm on page 10. So you understand why I'm trying to do here. One state of stress to another state of stress. Okay? All right. I'm assuming now Noriza Sahira is getting what I'm saying. Yes or no? Okay, got it. Good. So, I've been really slow here, right? Now, in figure 14.6, so I'm on page 10, all right? Now I'm trying to like move so fast in relation to figure 14.6 because I've explained all the little components. So after that, I can't help you much anymore, okay? So in figure 14.6, all right, if you have the picture, figure 14.6 is this, all right? And it will be nice if you can have it besides you rather than have it on both sides, okay? I have another of this figure here, so it's easier for me. On page 1410. Today I have a full class, 57. A few minutes ago I saw 58, so now I'm still having 57. So does that mean that if you go to the toilet, if you go for a pee, for example, right, you don't exist, it becomes 67? Is it sent, I mean, is it like automatically sensing you? No, right? So how come I have 56 now? So you have to like click yourself out, right? I don't know how, unless you leave the meeting. How do you leave the meeting, Abby? You have to like click yourself out, right? Yes, so how come now you have 57 and 56 a few minutes ago? Iskandar and Shah left, disconnected maybe. Okay, so that's like not by internet connection. All right, connection is the problem. So, okay, all right. Oh yeah, we can't do much about that, can we? We are at the mercy of this company. Now, I'm on figure 14.6. I'm on the last, I mean, at the bottom page of page 10, right? So, you know, when I showed to you earlier on that element, all right, sorry, the figure 14.6, I have U sub I and I have U sub F, right? And I said to you that one state of stress of the Moore circle to another state of stress of the Moore circle. Okay, if I have the total stress part and the effective, not the total stress. I have the total stress and the verticals and the effective stress separated by the U, all right, the pore water pressure. Now, these things, when I said to you the stress part, they are a representation of something that is happening in the field. And you remember when I initially said to you, what they're trying to do is that we have an element of soil, and at the surface, we're going to build our building. Now, I'm going to say it so simple as that. You're going to have your structure. You're going to build it on that surface. Your soil tend to be clay. And then if we consider it as an undrained situation, you have to do twice, drain and undrain if it's clay. And in the bearing capacity, you do both that analysis, you find the allowable bearing capacity, right, in the drain and undrained situation. And then now you have to consider the settlement. All right. So here's a picture here that the initial state of stress. All right. Here's the picture when I said that you have that Moore circle and you have all those states of stress. This is how you are trying to represent them. All right. So you have your element of salt. The water table is at the surface. You remember I asked you to draw earlier on this, all right, to get your head screwed right, so to speak. Okay. And then you have the pore water pressure. And you know how to calculate that static pore water pressure. Right? The static pore water pressure. U is just equal to gamma W multiplied by Z. You will note that the Z is to the center of the element of salt. All right? The element of salt now have the vertical stresses sigma 1 and the horizontal stresses sigma 3. We don't bother with the intermediate stresses sigma 2. All right? Because we are dealing with the principal stresses. Okay. So then you see that's the initial part. The initial part, nothing on top here, no building, no nothing. That's just your soil. Okay. Then on this part here, all right, same element of soil. Now I'm going to put my footing, my my buildings. All right. So from one state of stress to another state of stress, what happens to it? Okay. That is all we are trying to do. Okay. So I have that small element of cohesive soil, clay. Then initially I have that one, the pore water pressure and everything. Nothing else has changed. In the later part, the only thing that has changed is that I increased the vertical stresses. All right, because I'm putting a structure on top of my soil. So now that element has my building on top of it, which is going to stay there as far as I'm concerned until Armageddon, until the earth doesn't exist anymore. All right. So in other words, what I'm saying to you is that that load I'm applying is going to be constant. It's going to be staying there. Okay. What is going to change is the pore water pressure. What is going to change is also the settlement now. Because I'm not talking about bearing capacity in this topic. I'm talking about settlement. We have talked about bearing capacity before. All right. So there are always two things: bearing capacity, settlement. All right. So we finished talking about bearing capacity. In fact, you're going to give me the homework. But now we're dealing with settlement. So every time I'm talking about foundation, you must do bearing capacity. You must do settlement. All right. Okay. So now on page 11. All right, I'm on page 11 now. So referring to figure 14.6, figure 14.6. All right, referring to figure 14.6. Okay, so I have them here beside me. Now I'm going to be pretty fast because I've spent time with you on explaining what is happening. So it is just now to follow what I'm saying. All right. So if I look at on page 11, it says referring to figure 14.6, which occur on page 14.9. All right, figure 14.9. Okay, figure 14.9, I've got, sorry. And page 14.9 is where the description, what is on page 11 is just the summary of what you will find on page 14.9. Perhaps it's better for you to read page 14.9. And even better, a summary of all the summaries is to be found in Craig's book. Because I know that from my past experience, when I just explain Craig's book to you, to my student, they find it difficult to understand. So I have to spend a lot more time in expanding things in order that people can understand. All right. So what I am trying to explain in figure 14.6 and figure 14.7 can also be seen, all right, in a very summarized way on page 257. All right, page 257, the summarized version. Okay, if you can follow what is happening on page 9, 10, and 11, and page 8, then you can just probably summarize everything by Craig on page 257. All right. Usually some people find it difficult if they just read page 257 for the first and last time. So usually That's why you see page 8, 9, 10, and 11 just to explain page 257. All right, so I have M, which is the initial effective stress point. Again, that initial stress point, you have to look at the picture which I draw at page 10 at the bottom. This is the initial state. And then I have N, the initial total stress point, which is to, the other picture which says later. All right, and P is just the vertical stress increase following erection. Total stress part move from N to P because now I'm applying the stresses from top to bottom to my element. Now, if I have undrained, what is undrained? Undrained is just that you transfer the load that you apply to the solid, but the solid then transfer it to the water being the pore water pressure, right? And because it is fully saturated in the clay, the worst case scenario, all right, now it has an increase in pore water pressure. All that increase in pore water pressure, the excess pore water pressure, not just the pore water pressure. Water pressure initially has some value, right here, has some value. On top of that excess, on top of that initial pore water pressure, I have the additional load, which is now transferring to the pore water pressure, the excess pore water pressure. The soil doesn't like it, all right, this excess value, because it was having a whale over time, enjoying itself, nothing to disturb it at this time, all right? The at-rest condition, all right? The lepak version, okay? These people are enjoying it. And then you come and bother with the element of soil. You started putting some stress to it, okay? You put some stress to it. It doesn't like it. Now that excess pore water pressure has to be dissipated on drain situation. So unless that excess pore water pressure is dissipated, that soil is always going to be stressed. Right? So that's not going to happen. Nobody likes to be stressed forever, so it has to be dissipated. And dissipation of excess pore water pressure has to be through drainage. Right? Otherwise, pressure remains. Yeah? Pressure always remains in the cheek unless I release it. If it is released, then I'm back to normal. I'm not stressed anymore. Okay? All right. I know how many times I've already explained that. So, undrained. At the time of construction, it's very short compared to consolidation time. What is meant by that? Because you see, unlike my cheek here, when I release that excess pore water pressure, which is so quick, all right, to build anything on my soil, it takes about 3 years minimum. All right. Consolidation, you remember that observation? It took years to occur because it's so slow. All right, that dissipation of excess pore water pressure through drainage, so slow. All right. Why? Because the pores in the clays are very small. So small. This is big. All right, very, very small. Okay. You will remember the chapter 2, the table. All right. Clay has small pore. All right. So the dissipation is so slow. It takes years and years and years to finally make that cheek, like my cheek has nothing. The excess pore water pressure. Okay. So it's all relative then. 3 years in relation to the dissipation of excess pore water pressure is nothing. All right. In terms of application of pore water pressure. So, okay, short compared to consolidation time. So M remain unmoved. Effective stresses will be initially unchanged. Pore water pressure increase from U sub I to a value represented by distance MP. Note all these things are stress part. Note that when I say there is a change in this value represented by distance MP, sigma 1 may decrease, sigma 3 may increase. All right. You must have it in your head. Otherwise, they just like, what on earth is he talking about? Right? Okay. So, with consolidation, here's the thing that is being explained to you. With consolidation, you know what it is now. All right? That phenomenon. Okay? the increase in that pore water pressure. Okay, so sigma 1 remain constant, sigma 3 decreases. Why does sigma 1 remain constant? Because like I said just now, I'm not going to change my building. I'm not going to put my building, and tomorrow I'm going to remove my building. It's going to stay there forever and ever. All right, so it remains there. It remains constant. It's going to give to that element of soil by sigma 1 all the bleeding time. Okay, this is what is my head. Now, but as I'm doing that, my water pressure is increasing. Yes or no? Yes, of course it is increasing. Like I said a few minutes ago, it's transferring to my solids, and then it's transferring to my water in the pores. All right, so there is an increase in pore water pressure. That is why now the horizontal stresses, which is related to the vertical stresses, say some K naught multiplied by sigma 1, okay, that is going to be constant, but my pore water pressure is increasing. So my sigma 3 now will decrease. Yes or no, guys? See, now if you, okay, Akmal is following me, Abby is following me. Unless you got what I said a few minutes ago, you will find what I'm saying now nonsense. You see? Because every time I'm talking about a point, I'm talking about sigma 1 and sigma 3 and the pore water pressure. All right? And that's why, like I'm saying, these pictures all now remain important. And that's why I'm saying to you, right, all this, like just now when I say this point here, see, this point here at the top here, they are related to sigma 1 and sigma 3. What is doing the movement of this point is the sigma 1 and the sigma 3 and the pore water pressure. So if you don't have it in your head, what is increasing and what is decreasing, right, then you cannot follow what I am saying. All right? So why am I explaining this to you? Because after this, you are on your own. When you're reading this, right, and you find it still difficult to understand what is happening, relate to the idea that you have sigma 1, you have sigma 3. Sigma 3 is related to sigma 1. There is concentration. Pore water pressure is increasing. And at some point, this pore water pressure is going to be totally dissipated. I don't know when, maybe millions of years, but you know, as far as you're concerned, you can capture it in the stress path diagram with Q and P. All right, with Q and P as the vertical and horizontal axis. So that's all there is to it. Okay. Now, so then now my job is very easy. That's why I'm reading all this thing. Okay, just reading it to you and just saying blah blah blah. Okay, with consolidation. Now sigma 1 remain constant, sigma 3 decreases, then you get that stress path, P to R. All right, the point moves from P to R, but the point is a reflection of a state of stress. The state of stress in relation to sigma 1 being remaining constant, sigma 3 decreasing because pore water pressure increases. See? Okay, so I get P to R. And then effective stresses increases with dissipation of pore water pressure, but the effective stress, however, you know, increases because pore water pressure dissipates over time. All right, so it becomes lesser, and therefore sigma, the effective stresses increases. All right, so the effective stress part of K sub naught line is M to Q. You remember I said earlier on that this sigma H against sigma V, which is sigma 3 against sigma 1, and which is related to some K naught, all right, is a constant always. Well, you will see now that picture on page, where is it? On page 14.9. You have that 14.9, right? The K naught line. See? This 14.9, the K naught line is a constant. It's just a line which is with a constant gradient. All right, that M to Q. So you have definition of K naught line on page 8 just now, which says sigma H against sigma V is equal to K naught. That is a constant. It never changes. All right. Okay, so K naught line is defined as the locus of the top of the effective Morse circle. The top of the effective Morse circle, not the total circle, but the effective stress. All right. All right. Thanks, AB 14.9 here. The effective stress. All right. So which possess a constant ratio between the minor and major principal stresses. Page 13. Fine. Now I'm already on page 12, guys. Okay. So I have the effective stress part move along the K naught line for one-dimensional condition. Oscillation completes when excess pore water pressure fully dissipated and pore water pressure returns to U sub I. That is all being described in this picture. See, a lot of writing to just understand this picture. But you see, this is why we are engineers. Engineers with one diagram explain everything, if you understand what is happening. Otherwise, you have to write a whole essay and more essays to explain everything. All right? Okay, I'm done with page 11. Now, before I forget to explain it, let me say to you, this is what is happening when you go to soil mechanics lab 2 and you have that diameter, that ring of odometer. You put the soil in that ring, all right? And then you apply load, okay? And then you come over, say, 2 weeks. Every day you come and you try to get the settlement and you plot the settlement or M sub V or C sub V, whatever you plot, okay? The state of stress when you were doing that test is this one. This is the picture trying to explain to you the state of stress when you were in the lab, which is also what you say. I'm using this theory to calculate the settlement that is happening in the field. This is the one-dimensional conventional odometer method. Are we clear? Now I don't see Mira saying yes now. Only Abby is saying, only Iskandar is saying yes. Hi, Akila, how are you? Sasha Zukrina. Oh, okay, how are you, Sasha? All right. So, you see all this picture, kan? You know, this picture is just line. By right, it should just be a line. This is what the state of stress that you apply in that soil mechanics lab when you were doing that odometer test. And this is the state of stress, right, that is happening when you apply your load in the field, okay? And then you calculate for your settlement. All right, one-dimensional conventional state of stress. Firstly, I agree with you, you need a break. All right, okay. I agree with Fazli, we need a break. How long, Fazli? I'm talking too long, is it? Amy say yes. Fazli say 15. Moaz say 10. Mas, you are around. Okay, 10, right? 10, but after 10 minutes, I'll come back, all right? Okay? All right, time now is 3:35. I need a drink anyway. Okay, fine. I'll continue from page 12. Okay? If I have 58, I don't have to do a roll call. I should have done a roll call last week. Then I know who is absent. Today, everybody is around, it seems. Yes? All are here today. Right? So in that case, I will give homework every week then. Then I will have everybody in the class all week. I'll take a break for a while. I need to use the toilet. Kimi, where are you? Usually you ask, you are around and you say, hi, sir. Is he around? There are 54 people. The other 4 is gone, maybe. Hello, Kimi. Where can I see you guys? 54. Okay, Amma here, Kairina. I haven't heard of Karina for a long time. Adaha, I don't know who. When I look at this, then I realize Angela is also here. Yeah. Hakim Karim is supposed to be here, but I can't hear him. Anissa, okay, Azik. Yeah, no. Sure. What time did I say that we should be coming back? I forgot. 15 minutes, 35, 5, 10, 15. So in another 5 minutes. Razin, are you around? Hello, Razin. I do, but okay. Belum, 10 minit lagi, Mira. Coming to. Yep, you're here. Muhammad Fazli says 355. No, cannot be 355, Fazli. 350. 350. because 335, 5, 10, 15. 350 lah. Macam mana 355 pula? Okay, 350. Maybe we just finish with the stress part and then that's about it, right? And we don't bother with the settlement of structures and send this on because, well, I don't know. Let's see how it goes. All right. What time will we finish? Iskandar, 5 o'clock, maybe 6 o'clock. Well, I mean, Iskandar is asking me why 6, then I'm like saying that why not? Right? Iza Sahira says, please don't. Why? You're not enjoying it? Iza Sahira. Iza ni, what should I call you, Iza? Iza Sahira is very long for me. Nur Iza Sahira is even longer for me. So can I just call you Iza? Right. Yes. Okay. All right, I think we try to finish page 12. If I don't, explain it to you too well about it, I think you get the picture now, right? And therefore you can depend on yourself, all right? It's quite tiring to explain things over and over, right? But then again, it's my job, so fine, I'll do the best I can. Now, that's the one-dimensional consolidation test, right? Basically, it's like 1 minute to 3:50. So I'm just taking the liberty to start now, right? Because I think everyone is want to finish early anyway. But note, I have to collect your homework and say some stuff today. So anyway, that was for the stress part or the odometer test, all right? For the one-dimensional method. Now, again, when we were doing all of this from the beginning today, why are we doing this? We just want to see what is the difference between, right, the stress part and how it has bearing. Yes, how it has any any explanation as to why, all right, the way we stress an element, if there are any differences in the prediction of settlement. And why do we have to worry about all of this? Because we start with one-dimensional test and then we said to ourselves, well, we're not happy with that one-dimensional test result, the prediction. Skempton and Barham suggest to us that we have to use a different method for calculating the settlement. And then when we adopt this method, we realize that yes, there is improvement, but still, right? It's not a big improvement. We're still quite far off from the observed result. So we say to ourselves, then what is the problem? Okay, so Scantron and Barham says that the way we stress our element of soil also has some bearing on how the outcome of the result is going to be. So that's why now we're trying to like, okay, draw the stress path for one-dimensional. And if it is not one-dimensional, all right, the stress path is not one-dimensional. In other words, what is going to be occurring in the field, which is three-dimensional usually, all right, if there is any difference. And if we can see the difference, then we can then perhaps propose a different way of predicting settlement in the field. Now, you probably realize by now that even though we have to do many different methods for bearing capacity, all right, bearing capacity, we have many different methods. And also we are not too satisfied with just one method. You realize that it's the same with settlement, but with bearing capacity, it's relatively easier in the sense that, you know, you have all those different methods, but they are quite straightforward. Okay, you can do them, right? And they are not that far off in terms of their prediction of the bearing capacity. Okay, as you probably realize by now, right? When you know, after you've done the homework and I asked you to do the various different methods. Now, with settlement, you realize by now that it's pretty difficult, all right? That the prediction is quite far from each other, okay? So this is what usually is happening in the field, okay? You realize that the prediction of settlement is harder than the prediction of bearing capacity. And most of our problems in the field is because of the failures, if you like, right, are mainly usually due to settlement rather than bearing capacity. This is the actual things that are happening on site, all right? So very rarely you have failures due to bearing capacity. Anyway, moving from that, now we are looking at the consolidation, all right, where we don't have the one-dimensional odometer method, all right? The figure 14.7 is where the settlement is occurring. The stress path for a typical settlement occurring in the field. Again, the situation hasn't changed. All right. When I say situation hasn't changed, I mean that on page 10 here, you still have the same element of soil. All right. You still have the initial condition. Then you're just going to load the surface of your building. All right. Let's assume that we're going to load it at the surface. And what happens to the element? Okay. And then we are trying to capture these two paths, these two extreme, right? These two end condition, where this is one stress path, this is another stress path. For the one-dimensional consolidation test as represented by the odometer test in the lab, and also the other one in the field. So now I'm looking at figure 14.7, all right? Here's figure 14.7, which is in the field, okay? So M and N, all right, is the initial effective and total stress point. And you still again have the initial pore water pressure, okay? Now you probably realize by now that the figure 14.7 is different than figure 14.6, okay? Figure 14.7, you had the K naught line just now, and you have the sigma H and sigma V equals to K naught, and that actually is a stress path, okay? In figure 14.7, you notice immediately that it doesn't follow that line anymore, all right? So M and N is the initial effective and total stress point. That's just the state of stress in the initial condition, all right? And the pore water pressure is still there, U sub I being the initial, all right? The U sub I is just a constant, okay? Now you just want to see that the N, you have these two lines now, one for the total stress path, which is from N to R, okay, from one state of stress to another state of stress, and then the other one, which is M, O, and Q, The MO and Q is the effective stress path, all right? And the NR is the total stress path, okay? So, if you don't have figure 14.6, perhaps you quickly look at figure 14.6. I have figure 14.6 here, right? You see that they are different, okay, from figure 14.7. The NPR is the total stress path for the one-dimensional constellation, and then the MQ, all right, is the effective stress path which follows the K sub naught line in the one-dimensional constellation. So that effective stress path MQ, all right, is not the same as MOQ. All right, in the field, in the typical settlement field situation, you have MOQ. This one here, which is on the K naught line, is only M to Q. All right, and remember that Q is the top of the Morse circle and M is the top of the Morse circle, and they have sigma 1 and sigma 3, all right, plus pore water pressure. Okay, all right. So now we're just trying to explain, okay, what is happening. So upon erection of structure, meaning now you just you're just constructing your building, there is a change in the major principal stress, the total stress path N sub R, which is being reflected by that N sub R. So sigma 1 and sigma 3 is changing when you put that load on the surface of the soil. That's all they're saying. And then after erection, once everything is complete, all right, ESP moves from M to some point O. Okay, that means my building has completed after say 3 years. All right, there is no longer any sigma 1 changes. Sigma 3 may change depending on the pore water pressure. All right, so in fact it does. It says to you pore water pressure increase from U sub I to a value given by O sub R. All right, okay, total stress path and the total stress path that is just given by O sub R, the initial pore water pressure changes to the final pore water pressure, which is equal to excess pore water pressure plus the initial pore water pressure. I hope I am not losing you. U sub I plus delta U is equal to U sub F. All right? Okay. So, pore water pressure increase from U sub I to a value given by O sub R. O sub R is that change in the stress path. Then effective stress change immediately following load application, in contrast to one-dimensional constellation. I already alluded to you, I explained to you that MQ is not the same as MOQ. MOQ is where you find the typical settlement field situation. All right, and you notice this MO, because this change in stresses gives the immediate step settlement. This MOQ, all right, is where the difference in terms of the stress path. The MOQ, effective stress change immediately following load application, in contrast to one-dimensional constant, this change in stresses gives immediate settlement. So what are they saying to you? They're saying to you that in figure 14.7, the stress path that is being applied, all right, is able to capture. It's able to capture the compressibility that you call immediate settlement. And I've already defined to you what immediate settlement is. That is to do with the elasticity. All right, elasticity. In the one-dimensional testing, we are not able to capture this stress path as reflected to give, which results in the immediate settlement. Okay, so that's the main distinction. So from O, the effective stress path, I'm already on page 13. The effective stress path move horizontally to Q as excess pore water pressure, delta U is dissipated. That's the same, all right? That's the same as the one-dimensional constellation test. So the constellation completes when soil returns to its initial value, meaning U sub F now returns to U sub I. So the effective stress path from 0 to Q, constellation settlement takes place. So you have two in figure 14.7. You have one, the immediate settlement which is being captured, the stresses that are giving the immediate settlement, and then the other one from O to Q where consolidation settlement occurs. Second type of settlement due to the due to the dissipation of excess for water pressure. Okay or not okay? Right. So what am I trying to say? Just how to understand what is the difference, okay? What is the difference in the state of stresses when you load it in a one-dimensional state, like the odometer, or when you actually try to load it like in the field, okay? They are different. The stress part shows to you they are different because like I said earlier, Scampton and Theorem says to you how you know, whether it is normally consolidated or over-consolidated, will define to you what kind of settlement you get. So then we say to ourselves, how am I going to capture this? How am I going to show to you that, you know, these two stress paths are not the same, okay? And if I were to say, then I take the sample like in my case study, and I say that it is one-dimensional consolidation, when in actual effect in the field it is not one-dimensional consolidation, then I'm going to have problems. All right. Even though if I solve the problem using odometer test, I'm not going to get the prediction that is going to happen when I have that bungalow in the field. All right. So that's all there is to it. And I took a long time to come to that conclusion. You have to see that conclusion. So when you read, perhaps, okay, when you read that book, all right, when you read the book on page, what was it again? Okay. On page 257, right? It is actually on page 255, you see the title to be settlement by the Scampton-Barron method. We did that last week. And then this actually this picture of on figure 711, the stress part, right? When Scampton-Barron was trying to deal with all those modifications, okay? That picture is figure 711, stress part. So the AB there, you see the AB on figure 711 is the MO, if you like. MO on my, what is the MO on my figure 14.7. Now, Scampton and Barron explain it in 2 paragraphs, so perhaps you can now, when you read this chapter, it's easier for you to understand. All right, and then there is this figure here on figure 710. All right, the state of stresses of the element when they were trying to get the A parameter, the B parameter, and the the alpha and all of that. That was the state of stresses that was actually being applied, okay, in the triaxial cell. I didn't want to explain all of that last week because you didn't have this idea of the stress path and the history of an element of soil in being stressed and how we can actually represent it on a graph. So now I don't have to explain that figure anymore. Okay, so there is that example on page 1412. All right, the example 1412 is just to show to you when you make a prediction that is based on the wrong assumption, how far away is that assumption going to how do I say it? It's not that. So how is it going to make a big difference, right, in terms of the assumption? So I'm on page 1412 of my set of notes, right? I hope you're there as well. Hey guys, all right? Okay, I'm going to read the example. I'm on page 1412. Okay. And even if you have forgotten your constitution, settlement theory is still okay. It's just trying to show to you certain things only. All right. The example says a circular pervious footing having a radius of 1 meter is located on the surface of a clay stratum 10 meter thick. Okay, you have a clay layer, it's 10 meter thick, and then you're going to put a footing on the surface. Very rarely we put footing on the surface, but this is just, how to use tabs and table. Okay. Then you compare the value of T sub 90 for one-dimensional constellation with the value based upon the more realistic assumption. Okay, here you go. If you make the realistic assumption that the constellation is three-dimensional. All right, the one-dimensional is your odometer. All right. The more realistic assumption is to have it in three-dimensional. Okay. From your one-dimensional solid mechanics 2 test, lab test, you get your C sub V, which is 10 to the power of 3 minus, 10 to the power minus 3 centimeters squared per second. Then you have your three-dimensional C sub V, which is 5 times 10 to the power minus 4 centimeters squared per second. All right. So if you're doing your one-dimensional test in the lab, using that odometer ring, you can also do the three-dimensional test, but you're not going to use your typical one-dimensional odometer ring. You're going to do it in the triaxial cell. And again, so I understand it from you that you weren't, the triaxial cell wasn't demonstrated to you. It's, like I said, a shame. Anyway, moving on. So the time factors for the one-dimensional and three-dimensional cases may be taken from case 3 and case 6 constellation curves in figure 14.4. If you look on that picture on page 14.8, all right, they have all this initial pore pressure distribution for all the cases, all right? Not to be worried if you have forgotten this, all right? So for our problem, it says that you can have the you can simplify the pore water pressure distribution from the case 3 and case 6. So it's going to be case 3 and case 6. All right. Diameter 2A smooth blade. Okay. In figure 14.4. Okay. So the case 3 boundary conditions do not match exactly the condition in this problem. But they are much closer than the boundary conditions for case 1. All right. So case 3 and case 1 is almost similar, what they're saying. All right. But case 1 is the top layer, right? The surface is pervious, meaning that water can flow through. And then at the bottom is also pervious in case 1. Water can flow through, all right? Pore water pressure can dissipate. So that means the drainage part is reduced, right? As opposed to case 3, where the bottom part is impermeable, but the top part is permeable. So they're saying to you that the case 3 is better reflected, all right? But better still, of course, case 6, all right? Case 6 is smooth base, rigid, and you have this diameter, okay? Now, you have on figure 14.4, which is on the page 14.7, the different cases, and where T90 is. Yeah, you have the degree of consolidation and you have the time factor. Now, some 2 weeks back, I asked you if you have forgotten about the consolidation, one-dimensional consolidation. I said you better find some time to review it. In fact, I reviewed some things with you, right? When I did that one-dimensional consolidation on page 2A, 2B, 2C, and 2D. So if you haven't done that, it's time you find the time to do it. Now, anyway, okay, in this example, what was wanted to be shown to you is that if you make the assumption of one-dimensional and three-dimensional, as opposed to three-dimensional, which is a more realistic situation, you will find that the time for 90% of consolidation, all right, to occur. In other words, the dissipation of the excess pore water pressure to be 90% completed. All right, you're only left with 10%. And 90% of pore water pressure consolidation to be completed is not too bad, because, you know, if you wait for the other 10% to complete, it will be forever, right? You probably would be finishing the job anyway. So 90% is almost as good as 100%. And you notice in the one-dimensional, for 90% of the pore water pressure to be dissipated and thus the settlement to have occurred at 90%, all right, it is almost 23 years, all right? Okay, so it's almost 23 years. If you, however, make the realistic assumption that it is three-dimensional, that is what is occurring in the field, it is only 2.5 years. You see how far the difference is? You know, one says to you, you will only get 90% complete. Last they say fully completion. Okay, settlement will be fully completed in 23 years, you say. And the other one says to you, in only 2.5 years. That's like almost 10 times, right? Why is this important? Because if you're going to wait for the consolidation to occur in 23 years, all right, that means you cannot go into the house yet because it's still settling. You see? But actually, the real thing says to you, after 2.5 years, you can go and move into the house. It's like COVID-19. You see, you have all this model, right? Okay, you have all this model, all sorts of model. They tell you that if you have lockdown, you know, you have lockdown, okay, you probably get the, you know, the virus, not the virus, you get the spreading of the virus to finish in May, see? All right, fully complete lockdown, say. And then, you know, the same model will say to you that, okay, if you have like partial lockdown, you probably get it in June. And then another one that says if you do nothing, you get 600,000 people dead. All right? I think you have seen any these models, right? You are aware that they have all these models. Say something to me. Are you aware of all these things? Hello? Akmal says yes. Akmal seems to know. Muaz says yes. So that's why they have all this. Akila says yes. Okay, Akila, good. You know, that's why you are like aware of this flattening of the curve, right? They are trying to say to you that, look, we have to do this, or otherwise, right, we have 600,000 people, you know, being infected, and some of it cannot get into the hospital, right? Okay, so that's why we have to do this. All right, they are not trying to say to you we can, you know, we can stop the virus from occurring. Right, there is going to be infection, and you, as you probably know by now, all right, China, which says earlier on, they say we probably have beaten the virus. They are not around. That, you know, 2 days ago they find that, you know, they find that there is another cluster in Beijing, right? And they cannot figure out where this come from, because those people were found to be not going out of Beijing. They haven't gone out of Beijing. All they did was went to a market called Jinfandi market. All right. Now there are theories that you can actually, because when they do all the testing, right, then now they say, okay, we're going to lock everybody out, you know, this area around Jinfandi. Okay, market will lock everybody, we're going to test everybody. Well, China can do that, right? They have a lot of equipment. So, and they find out that, okay, you know, we have this cluster, but they haven't been out of Beijing, and they, you know, they've been staying in Beijing. And then they test the equipment, and they noticed that the virus was on this equipment. And the equipment was to do with the, you know, how this Jinfandi market is importing, all right, salmon and all this cold food, you know, salmon. I don't know whether you eat salmon. I do. So now I'm not going to eat salmon anymore. Okay, so salmon, and they suspect that because when they tested the virus, I'm talking about models now, but I'm giving you the details, right? When they tested this equipment, all right, they saw that the virus is there, and then they you know, they do this genome sequencing. They look into the RNA and the DNA, right? Well, virus doesn't have DNA; they have RNA. They find out that the virus is from Europe, whereas China had its own virus. The Chinese virus and the Malaysian virus is the same type. Okay, the one that is in Europe is a different type. Okay, but it's also coronavirus. It's not strain A. I think it's called strain B. Now the funny thing is that nobody went to Europe during all this lockdown, but the virus was found on the equipment. So now they are saying the theory. They're saying that, okay, when they imported those salmon, those cold fish, all right, Akmal said yes, different virus strain. They imported the the cold fish, the salmon and all. By the way, salmon and all these are good nutritious food, right? It gives you all this well, let me just say wonderful stuff that can make you healthier. Okay, so what is now the theory is that they, because when you import this stuff in cold, right? Because you need to store them, right, so that they come fresh. Well, by the time they come to China or Malaysia, all right, and then you put it on the supermarket shelf. Okay, right. Now it seems that you could be importing them because when you had the fish, right, the salmon and all those fish cold, you're also freezing the virus. And so when they release it in the market, so the virus was released. So that is one theory. The other theory, of course, they're saying that somebody, we don't know who, we never detected them, right? And then he came to the market, and then he sneezes, and then he went off, okay, and somebody got it. So now, what is my point to telling you all these models? Models are only as good as the data. Unless you get real data, you don't know how good your model is. You see? But it helps in making prediction. It helps in what to do. Right? What should we do now? Lockdown, don't lockdown. Shall we open the economy? If we don't open the economy, everybody is going to be dying soon. If not from the virus, they don't have any food to eat. Okay? So models have a purpose. You can see this now. But it is not, exact. It is a function of the assumption you make. This is what I'm trying to say to you. That's why when you learning about soil, sometimes things are difficult because we are depending on making prediction. And that prediction is a function of, again, the site investigation. All right? I try to impress upon you why it's so important making the right decision on your soil investigation. But of course, I said it's pretty difficult because you never actually had the experience, but I don't expect you to function like an experienced person. On the other hand, I do expect from you to put some thinking, okay, not just be a parrot, okay? That I impress upon you. And these things, the site investigation keep repeating itself. You get the wrong C and phi, your bearing capacity is not going to be good, right? And if you make the wrong odometer test, instead of it being a three-dimensional test, your settlement prediction is not going to be good. That's why we're learning all these things. All right? So you see that? 2.5 years and 23 years. So it's the same like you being locked down. You want to be locked down for 1 year, or for 2.5 years or 23 years. Get what I'm trying to say to you? Yes or no? Shasha Zukrida Imran now say yes. See? Otherwise, guys, I wouldn't bother trying to explain to you this theory, the point, what it means and everything. You see? Anis, long time no here. Yeah? Okay. So, that's the example, right? So, if we now know, right? Okay, if we now know that there is an influence of the three-dimensional aspect, all right, that is not constrained in one direction. If we know that the stress history is important, all right, So, and we want to predict settlement. How are we going to do it? You know? Okay. So far at your level, all right, after that example, you notice that on page 13, it says, okay, we need to take into account of the stress history. Then what Lamb now suggests, okay, you say, forget about this. Forget about this, forget about all the theories. We go and sample the soil. Okay, A, he says. Part one, he says, go and sample the soil. Then from the geology and also from the history of the element of soil, we do the calculation. Once upon a time, it was this far down the surface of the soil. We know the vertical stress is going to be this, and then we say to ourselves that perhaps it's a K0 condition. We find the sigma 3, so we then estimate, okay, the stresses and the initial condition. Then we say that now we're going to put this our building, which is about this load, these stresses, okay. We can find the dead load, we can find the live load, and then we're going to transfer to the element of soil. So we take the sample and then we put it in a triaxial cell, then we apply what we want to apply in terms of the field condition under three-dimensional condition. All right. So then we find the element, so we find under that load what the settlement is. And we do this in the triaxial cell. All right. And we repeat for all the elements. See in that picture there, I have 1 element, 2 element, 3 element, 4 element. Okay. I sample them at each of this, and then I apply all those stresses. Okay. I have the major principal vertical stress. I have the major vertical strain. All right. And I do that a couple of times. So a few minutes ago, I talked about the virus, and I said that we have this model. We have a model without doing anything. How many people will die if we do something? When do we expect, right? We can come out of that lockdown or whatever, okay? And then will it be above the hospital beds that we have, right? So we're trying to do 3 or 4 things on computer, and then hopefully we can come up with a good decision. Well, in this one here, all right, we take 3 or 4 samples, we do the test, all right, and then we find the settlement, right, from each of these elements, and those elements come from different layers of the clay stratum, all right. Then we just add them up, all right, and we just add them up in terms of the settlement, and that's what it is at the bottom here. The settlement says, you just do the integration for. If you get one settlement from one element, then we just do the integration. So what's the difference here? The difference here is that we are doing it like soil investigation now, but we are doing it in a more enlightened way. We are doing it in an intelligent way. We are saying to ourselves, not just the one odometer test, we are saying that we have to take into account the stress history, and then we try to replicate, we try to represent it in our triaxial cell, and then get the settlement. Of course, we do the calculation as well. We do the one-dimensional odometer calculation, we do the Scamton-Theorem calculation, right? I'm going to stop there. Do you understand what I've been trying to say to you today? Now I don't get any response. I understand if you have to, like, maybe read up a little bit, try to explain to yourself. Okay. Yes or no? Okay, guys. Hello, are you around? Or I am being disconnected. Muhammad Iram say okay, Shasha says okay. Yeah, fine, good. So I said to you that maybe I will go into settlement of structures on sandy soil, but I think it's already almost 4:30. I think we stop here. I try hard to understand, so maybe need to read the book. Yeah, Fazdi. All the time you have to read the book. Where's Amy? Amy, what does I say? Read the what? Amy, read the what? Imran says read the book. Not good enough. I don't say, Amy says read the damn book. Right? But Fazli, you get a bit of what I am trying to say. Yes or no? Yes. Okay. That would be a start, right? Then, okay. All right. AB also say yes. So, okay, right. Now I think we do the settlement of structures on Sunday. So, inshallah, yeah, God willing, next week we continue. And hopefully we finish on settlement, all right? What I'm trying to impress upon you is that why we do all these methods. In some years I get a cohort, they say, why do we have to study this? Why do you have to study that? It's confusing me. I say, well, you can take this one method and then be good with it. But the one method is going to give you all the problems. See, that's the problem. Right? It's like the virus. You don't know anything about it. Now you have soil, you don't know anything about it because you didn't do good site investigation. And sometimes when you do site investigation, we do the wrong thing, right? So that's just the problem. It's unlike concrete where you can, like, almost be sure what the value is going to be, right? Okay, moving on. I have a couple of things to finish up with you today, yeah? Which is, I have to talk to you about quality control and all that. And then I have to talk to you about homework, right? Collect the homework. By the way, I can give the settlement homework as I go along. Or would you rather wait until I finish everything, then, then you do the homework and give it to me, like bearing capacity. Shasha says, wait. You know the thing about when you wait, I hope, my assumption is that you will find the time to read, find the time to make it that you, to find the time to make yourself understand. Nobody can make you understand except you yourself, right? But if you wait and you don't use that time, right, to read the book, to reflect on it, then it is a waste to you, all right? And in the end, it's going to cause problem to you, not to me. All I'm interested is you learning, right? So that's my assumption. See, I'm giving that time, but I hope you don't abuse that time. We wait and read the book, sir. No worries. Okay. All right. But sometimes the homework helps you, finish everything on the topic, then we can do the homework. So, okay, fine. All right. On the weekend, I was on a webinar. You have seminars, but they call it webinar on the web. And this webinar on Saturday was an international webinar, and it was in relation to accreditation. All right. If you don't know, if you have forgotten, I'll just remind you, your degree has some quality control in it. In other words, right, for you to register with the Board of Engineers in Malaysia, and for it then, okay, to function as an engineer, right, in order that you have a name card. When you work, and name card says I'm an engineer. I don't know what engineer, but engineer, right? It could be any engineer, right? But engineer with an XYZ name. For you to be able to say that you are an engineer on a name card, your degree has to be accredited. Your degree has to be recognized by the Board of Engineers. And that's why we have all this learning outcome and everything, right? And ISO to ensure that you can be registered as a graduate engineer. And after that, for you to get, if you want to be a licensed engineer, you call yourself a professional engineer with a practicing certificate. Then that one you have to sit for another exam, a real exam, not a real exam. Exams are all real. Exam whereby, you have to pass it and then you get to be a PEPC. If you just only want a PEng, they have changed the rules. You want only just a PEng, then you don't have to sit for that very rigorous exam, because for the PEPC, for you to sign and make submission and to be responsible for it. I am a PEPC, right? So for you to be responsible for it, all right, and if you are not responsible, I mean, if you are responsible and you can sign it, so if there is something wrong with, say, the building or the soil or whatever, right, you sign, and it is due to you because you approve it, then they can put you to jail, all right? So, okay, for you to be registered as a graduate engineer, no big deal. You have to just have a degree that is recognized by the Board of Engineers. So that's what accreditation essentially is all about. Now, I was on that webinar, okay, and it has international recognition, all right, because your degree is, if Board of Engineers